Hello everybody. Today there will be a very interesting question on op-amp where it has been asked in 2024, where you have seen that it has been said that this circuit has both positive feedback and both negative feedback, but it is said that the circuit has to show sustained oscillation. So now we have to find out that what is the value of R1 and what is the value and what will be our corresponding frequency of oscillation. Okay, so let me first tell you, there has to be a sustained oscillation. Then what is needed? Then the circuit has to follow Barkhausen criteria. And what is that Barkhausen criteria? It says that the magnitude of A beta, which is my loop gain, that has to be, that must have a magnitude of unity, and that must have a phase of 0 degree or say 360 degree. Okay, where my A is the closed loop configuration of this op amp, where you can just assume that an input has been applied at the positive terminal, and beta is my feedback factor, which is my positive feedback over here, which is coming from the output to the positive terminal. Okay, suppose there is a little bit of noise has been generated at the output node, that will come towards the positive and then it will generate the sustained oscillation. And for that, these two conditions, which is mod of A beta equal to 1 and your phase has to be 360 degree, but it is applicable only at one point of frequency. Okay, which is my oscillation frequency. Let me clear one fact, that here I have said that my closed loop gain of this non-inverting amplifier is equal to 1 plus R1 by R, but that is only applicable when there is a you can say that the error between the two inputs of the op amp is 0. Okay, so only then your whatever the voltage which is over there at the V plus, that will be also the same at V minus, because your error is 0. Okay, so only under that condition we are making these two inputs equal and we are getting this closed loop gain, and we are not considering the feedback factor. Okay, we are adding the feedback factor, the positive feedback, and because of the positive feedback we are getting the sustained oscillations also. Okay, if you look into the feedback path, okay, which is coming from the output to the positive terminal of the op amp, there you will see that that if there is say current I0 which is flowing through this capacitor, which is at from V0 to V1, the same current is not going to flow through the other capacitor. Okay, and if you also see the voltage across these two capacitors, which is VO minus V1 and your say only V plus, then also you will see that those are not equal. So naturally it's a second order circuit because there are two effective storage elements. So this you should have to keep in mind, that this feedback factor is a second order circuit. Okay, and definitely it will have two poles, that we will discuss that how we are coming to this. If we consider this path, then we will see that say from node V1 there is a R and C, these two are in series. So if we compute the impedance in this series path R and C, then we will see that when, and it's an asymptotic Bode plot, that when the frequency is, means the angular frequency, which is my omega, is much lesser than 1 by RC, then it is behaving more of like a capacitor and the maximum voltage is appearing across the capacitor. But when my omega is much greater than 1 by RC, then you will see that this series of R and C, that is behaving more of like a resistor, and the transition is taking place when omega equal to 1 by RC. At that time you are getting a 0 over there. Okay, means your R and C, that if you compute the impedance, then it will be a 0 impedance, it will be a short circuit, so then only you can get a 0. Okay, that is evident from our Bode plot. Now if you look into the other part, that there is a parallel combination of R, and then from V1 to V plus, you can see that from V1 to ground, actually you can see that there are R and C which are in series. So now if you are seeing that both are in series, so what you are going to do, you just compute it in terms of admittances. So if you compute it in terms of admittances, then you will see that the combination of R and C in impedance, what is that? It is 1 plus SC plus R. So it is like 1 plus SCR divided by SC, and now you just do the reciprocal. Okay, then you will get the admittances, and when two admittances are in parallel, then you can just add it, and then if you do the reciprocal, then you will get what is the Z equivalent. Just derive the transfer function for the feedback path. We need to find out that what is the ratio between V plus and V0. But before going to that, let's replace this R which is in parallel with R and C. Let's replace this combination with R into 1 plus SCR divided by 1 plus 2 SCR. So V0 to V1, we are getting a voltage division. See, at V plus there cannot be any current which is flowing into the non-inverting terminal of the op amp. So across V1, the combined impedance which we are getting, that is directly connected to ground. Okay, so this is the transfer function, which is the ratio of V1 divided by V0. This we are getting, and over here also we are seeing that there are two poles also. Now our aim was to find out the ratio between V plus divided by V0. That is our intention. So what we need to do, we have to replace the V1 with V plus. Okay, so our feedback factor, which is V plus by V0, is nothing but SCR divided by 1 plus 3 SCR plus S square C square. Now this is my feedback part. Now we are going to utilize this beta, which is V plus by V naught, in our Barkhausen criteria, which is a mod of a beta equal to 1. So a is already 1 plus r1 by r, and my beta is SCR divided by 1 plus 3 SCR plus s square c square r square. Now if you just replace the s with j omega, then what you are going to get? We are going to get j omega cr into 1 plus r1 by r whole divided by 1 minus omega square c square r square plus 3j omega cr. Now when my omega is equal to the oscillating frequency, the magnitude has to be 1 and my phase has to be either 360 degree, or that is equal to our 0 degree. So we have to, so say our real part, which is in the denominator, if we just make it 0, then this 3j, and in the numerator there is a j, so this jj is going to cancel. So anyhow we are going to get a total real part. Clear? So that is how, if we just put 1 minus omega square c square r square equal to 0, then the omega oscillation that we will get as 1 by cr. Okay, and what you need the gain, means the loop gain magnitude to be 1. That is only possible if your 1 plus r1 by r is equal to 3. So your r1 by r is equal to 2. So your r1 is equal to 2r. So you have got the answer. Generally what we used to do, we used to just put r1 just slightly greater than 2r, so that we just always put the mod of a beta slightly greater than 1. But anyhow it is going to fulfill the Barkhausen criteria, because even if you just design in such a way that your mod of a beta is equal to 1, then because of some complication it might be less than 1 and there cannot be any oscillation. Because in your oscillation, if you go through that positive feedback loop, then in the denominator there will be 1 minus a beta. So your a beta has to be completely 1. But in practical it might not be. So that's why, as a layman rule, what we used to do, we used to keep a beta slightly greater than 1. I have another solution which you can do if you do some asymptotic assumption, say the Bode plot, and you just do the frequency analysis through Bode plot and through that asymptotic assumption. And if you do asymptotic assumption for this feedback network, then you can get an overall 3 dB frequency. Okay, but in reality it might not match with your original oscillation frequency. So I am just giving you a brief that how I have achieved to that point, then you can actually go to it. And also, if you just visualize this feedback network, so from V0 to V plus, your total phase shift has to be 360 degree. So if you can achieve it, under which condition which you are achieving it, so that will give you the exact answer for the frequency of oscillation. You can proceed with it, but today in this lecture I am not going to discuss about it. Here I have already explained that how you can go, but right now I am going through the frequency analysis, which you can just see. It actually helps in analyzing while you are doing any kind of circuit analysis. Okay, this is a very interesting topic, so let's discuss. From our intuition, this Z equivalent is nothing but which is I mentioned here as Z parallel. Here the black line defines that the series combination of R and C. It is a Bode plot. Okay, and for series combination, always remember the higher impedance always dominate. Okay, as we have seen in the previous slide. Now this series combination of RC is in parallel with the resistor. Okay, so now what is going to happen? The minimum impedance is going to dominate. So out of this C and this R, which is lower, the R is lower, and when omega is much greater than 1 by RC, then the series combination of R and C is behaving like a resistor. So if two resistors are in parallel, then it is R by 2. So there is a 3 dB drop. So this is my Bode plot for Z parallel. Now from the output V0, the capacitor C is in series with my Z equivalent, because there is no current which is flowing into the positive terminal. So it is a series combination, which I said as Z0. And I have already said that the maximum impedance is going to dominate when there is a series connection. So now what you are going to do? So you have to first plot that what was my Z parallel, which is my Z equivalent, which I have said. And then you have to see that this is my capacitance. So first what you are going to see, that when the C and the Z equivalent are in series, then the cutoff frequency is 2 by RC. So from V0 to V1, if we see that this is a high pass filter basically, okay, and we have already said, so what you are going to do, because when your omega is much greater than 2 by RC, then this combination of Z equivalent is appearing like a R by 2. So that is why I said that this is a high pass filter. So when my omega is much lesser than 2 by RC, then my minimum V0 is appearing across the Z equivalent and the maximum V0 is appearing across the capacitor. Okay, so at V1 I am getting almost 0 voltages when my frequency is very less. Okay, and when my frequency is much higher than 2 by RC, then all the drop off from V0, which is actually my feedback, which is coming from the output, that is appearing across the R by 2. Okay, so now there is a high pass filter now from V1 to V plus, there is another low pass filter. So now if you see that the cutoff frequency for the combined one from V naught to V plus, that has a cutoff frequency of only 1 by RC. And that is my frequency of oscillation. Here what I have done, here I have done some asymptotic assumptions for which we are not getting two poles. Generally we are about to get two poles when there is a second order circuit, but we are not getting it because I made many assumptions. So this process might not be efficient or might not be correct also to find out the correct frequency of oscillation. Okay, generally there has to be two poles that we are not getting because of this asymptotic assumptions. Okay, so it is just another method which I have shown you, but I am not giving there is no guarantee that you will be able to get a correct solution.